short section, what I want to explain to you is what the effect of a good leaving group, that is, of a halogen, on an organic compound is. So I'm going to call it I say the effects, I mean the reactions that result from the presence of a good leaving group. So going back once again to this organic molecule, we're saying that we understand that chlorine, or I should more precisely chloride, chlorine plus a pair of electrons, is a good leaving group. It's willing to let go of the carbon. So the first reaction is what's called a nucleophilic substitution. I'm going to have to, so I've just erased and moved some stuff up here. So I guess I've changed the compound. Actually, this is the one that I started with. 2-chloro-4-methyl pentane. Now, what I'm explaining right now is in the chemical reaction with a nucleophile. Now, nucleophile, you learned a couple of seconds ago, is a chemical species that has a pair of electrons that it can use to form a bond to a carbon. And often, not always, but often, a nucleophile has a negative charge. And generally, the strong nucleophiles have negative charges. So, in the reaction of a nucleophile with an alkyl halide, I'll use curved arrow notation. I'll say that pair of electrons can attack that carbon and push that good leaving group, that is chlorine with its pair of electrons, away. So in those two curved arrows, a whole reaction is implied. And in fact, the result, the product of the reaction is implied. Now I'm going to draw the 5-carbon chain a little bit differently. 2, 3, 4, 5. Over here there's a methyl group. And now there is this new bond between nucleophile, which is blue, and carbon, and a second product in red is this, plus chloride. It's pretty clear, I think, why it's called a nucleophilic substitution. A nucleophile substitutes for the halogen in an alkyl halide. As the nucleophile approaches the electron-deficient carbon, that's an important phrase, we identify the carbon I'm pointing to, the carbon that bears the halogen, is said to be electron deficient. The electrons that it's sharing with chlorine are not shared equally. The chlorine, because it's more electronegative, has sucked the electrons towards it. So the carbon is left electron poor or electron deficient. So the electron deficient carbon receives the electron-rich nucleophile and forms a new bond now, represented in that red bond, and it let go of the chloride anion. Nucleophile has substituted for chlorine in the organic molecule, a nucleophilic substitution. There's a second reaction, 2 basic types. The first I've just described in the last couple of minutes is a nucleophilic substitution. A second reaction is called an elimination reaction. Elimination reaction, the reagent is a base. Now, it is nearly always, I think it's always the case, that the base also has an unshared pair of electrons, but because it's a base, it uses that unshared pair of electrons to receive a proton. So the reaction would be this. Now notice, I have the halogenated carbon on carbon 2, and I've written in what was there all the time, but usually not expressed, but now they're expressed, is that on the carbon bonded to the halogenated carbon, the carbon next to it, there are 2 protons. Now, in this reaction, the base will abstract one of those protons on the carbon 1 bond away from the halogenated carbon. And this is what happens. The base does what a base does. It grabs a proton. It forms a bond to that one. Now, in this reaction, the pair of electrons that at this moment is bonding the hydrogen to a carbon, that pair of electrons moves up here, and the pair of electrons between the halogenated carbon and the carbon leave with the chlorine. So in this case, there are 3 curved arrows. All these things happen at once, in one step. A base reaches out to form a bond to proton on the carbon adjacent to the halogenated carbon. The pair of electrons linking that hydrogen to the carbon become free and form a new bond, a second bond between carbons 2 and 3 of this molecule. And at the same moment, halogen with the pair of electrons that it had shared with the halogenated carbon leave with the chlorine. So the result of the reaction is the same, basically the same carbon framework, 5 bonds, 5 carbons, 1, 2, 3, 4, 5, 1 up here. And now there's a double bond between carbons 2 and 3, and a small molecule that has left is this, H, in this case, Cl. It's called an elimination reaction because a small inorganic molecule is eliminated from the organic compound. And the organic compound is converted from an alkane to an alkene, an organic compound with a carbon-carbon double bond. Again, one more time in contrast. When we have an alkyl halide, now I've written the same alkyl halide twice. It's with the 4-methyl-2-chloropentane. In this case, I'm going to demonstrate what happens if methoxide, which has a pair of electrons available for forming a bond to a carbon, when it acts as a nucleophile. If it acts as a nucleophile, it takes that pair of electrons and identifies a halogenated carbon, a carbon that has a good leaving group, and kicks that halogen away. Now, the result of this, I'll try to draw it small because I don't have that much room, is the same framework of carbon atoms, but now we have halogen gone, and I'll draw it down below here, that methoxide, the nucleophile, has formed a bond there. And the byproduct is a chloride plus Cl minus, the leaving group. Chlorine has left. What had been 2-chloro 4-methylpentane becomes 2-methoxy 4-methylpentane. In a different circumstance, the same reagent, methoxide, if it behaves as a base, that is, if it abstracts a proton, the reaction would be this. The methoxide would look for a proton on a carbon adjacent to the halogenated carbon, free a pair of electrons from that to form a pi bond between the 2 carbons, and displace the chlorine again as a chloride. The result of that reaction, of those 2 curved arrows, would be the same carbon framework, but now a double bond between carbons 2 and 3, and the loss of an H plus and a Cl minus. So we could say that the byproduct is H plus Cl minus. The first type of reaction is called a nucleophilic substitution, and the second type of reaction is called an elimination. The exact circumstances of which will form, or circumstances in which both will form, is stuff you'll have to learn about. There's some nuance, and we'll get an idea of what kind of chemical species was much more likely to act as a base than as a nucleophile, and what kind of alkyl halide is more susceptible to substitution or to elimination. But that's the details of the chapter. The high-level view is what I wanted to express in this video. Thank you.